The following, which molecule has the largest bond angle? Largest bond angle. Okay. And we've got more than one have equal large bond angle. Okay. This is more than. So we got water. We got HCN. We got OF2. And we got ozone. Okay. If you're in a real hurry, you need to remember what we did for each one of these. Let's see. We've done that one, this one, this one. I don't think we've done this one. So if we draw the Lewis dot structure and use VSEPR to find out what the geometry is, then we can predict the bond angle. So this one is 2 times 7 is 14 plus 6 for oxygen is 20. So we put oxygen in the middle, fluorine on either side, that's -4. 16 left over. 2, 4, 6, 8, 10, 12. And that's 4 left over. So we got 2 there, 2 there. Okay, around this central atom is going to be 1, 2, 3, 4 groups, which is tetrahedral, right? And that bond angle is 109.5 degrees nominal. But we're also going to have, if you draw a representation of that, you have, say, fluorine in the back, and then a fluorine over here. And then you have a lone pair there and a lone pair here. What that lone pair is going to do is compress this bond angle. So it's actually less than that. If that makes a difference later when we assess the rest of them. Okay, how about ozone? 3 times 6 is 18, right? So we have O, and O. 4, that's 4 is 14. So 2, 4, 6, 8, 10, 12, 14, right? 2, 4, 6, 8, 10, 12, 14, 16, 18. So this is going to be a trigonal planar. And what's the bond angle for that one? 120 degrees. Except with this lone pair sticking up there, it's going to compress that bond angle too, so it's going to be a little less than 120. How about this one? HCN, do you remember that one? Do we need to do that one longhand? Hydrogen cyanide, sure. 1, 4, and 5, right? So we have 10 electrons. HCN. So that's 4, gives us 6. Can't put any more around hydrogen, so we work from the outside in. 2, 4, 6, right? Got all of our electrons placed. Now we got to make an octet if possible. So in order to make an octet without robbing one from the other, we'll put 2 here for that bond and 2 here for that bond. And we still have 2, 4, 6, 8, 10. So this is linear, 180 degrees. Okay. And you remember water is tetrahedral. It's kind of like, yeah, it's kind of like this one. It's like that, like that. It's a bent molecule. And it's less than 109.5. Because these 2 lone pairs up here do what this one does, compresses that bond angle. Now, we don't know how much it compresses the bond angle. So we can't really say that this one's the same as that one. Although, I guess that would be a viable choice. Except that the largest bond angle is obvious. That one right there. 180 degrees. If this one were missing, then we might pick E for these 2 being roughly the same. Okay, 34. I cleaned the board with furniture polish earlier. It's erasing better. Which of the following molecules is non-polar overall? So we have through E, A, B, C, D, and E. And we have SF4, SF2, we have carbon tetrachloride, H2S, and we have OCl2. Okay. So we need to know two things. Are the bonds polar? And what's the geometry? Right. The bonds are definitely going to be polar for these guys right here because fluorine is the most electronegative element in the chart. So we know those polar bonds, polar bonds, polar bonds. Okay, so they all got polar bonds. We need to know the geometry. All right, so sulfur is 6. 6 plus 4 times 7 is 28, which is 34. So we got a sulfur in the middle. We got fluorines here and here and here. That's 2, 4, 6, 8. It's 26. Got 26 electrons left over. 2, 4, 6, 10, 12. And 12 more makes 24. So we have 2 electrons that have to be placed here. Right, this is not symmetrical. This is 1, 2, 3, 4, 5 groups, which is a trigonal bipyramid. Right, when we draw the trigonal bipyramid, we have a triangle in the middle, and we have one up here and we have one down here. And we have in the middle, we have the sulfur. And we're going to have fluorine there, fluorine in the back, fluorine here, and there's our lone pair. Remember, in the trigonal bipyramids, lone pairs go on the triangle. So what that gives us is, if we look at the bond, actually here to here, turn it on its side, you have a seesaw, right? And that's asymmetrical. If those bond polarities are pulling this way, this way, this way, and this way, there's nothing pulling this way. So our overall dipole moment is about like that. Right? So, and we're still looking for the non-polar ones. Okay. How about this one? 6 again, and this only has 2. So 14 is 20. So we have S and then 2 fluorines. So that's minus 4 is 16, 2, 4, 6, 8, 10, 12, 14, 16, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay. So we have 4 pairs, 4 groups around the center. This is tetrahedral. And if we draw the tetrahedral structure with this, it's like water. Like water has oxygen, oxygen, hydrogen, hydrogen with 2 lone pairs in the middle. So it's going to be bent like this. Right? And that's a dipole moment. Actually, I'm not sure what the dipole moment is because we have lone pairs here, but we have dipoles there like that. So whether the fluorine wins out or the lone pairs win out is your guess as good as mine, except that there is going to be an imbalance. So this one's polar, this one's polar. This one is carbon tetrachloride. Carbon is 4. 4 times 7 is 28, which is 32 electrons. So we have carbon, and then all these chlorines around here, here, 2, 4, 6, 8, which is 24. 2, 4, 6. 6 times 4 is 24. So if you finish putting the electrons around here, that's it. They're all used up. And each one of these is a dipole moment toward the chlorine. Right, just look at where the carbon is versus the chlorine. The carbon's there, chlorine's over here. So it's the dipole moment is toward the chlorine. But 4 groups is tetrahedral. And every position in the tetrahedron is taken by an atom. This is perfectly uniform. So all the dipoles cancel out. This is nonpolar. We found our nonpolar one. We could look at the others. H2S is like water. Okay. S is right here under oxygen. It behaves the same way. Like that. So it's polar. And then OCl is, I think it's like this too. Cl. Let's see, we've got 2 times 7 is 14, plus 6 is 20. So we got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Yep, it looks like water also. And this is polar also. Okay. So the only non-polar one in here is carbon tetrachloride. That's why they used it to clean your clothes before the EPA and OSHA shut them down. So they had workers that were getting cancers from using the stuff. So they made them stop using it. They had to go to something else to dry clean your clothes. Something more expensive, of course. Let's see. Yeah, C. The answer to that one. And 36 coming up. Which of the following molecules are linear? Okay. So what do we have to choose from? NO2 minus, the nitrite polyatomic ion. And we have C2H2, which I'll bet my money is acetylene. And then N3, which is, this escapes me. HCN. Azide. That's the azide ion. Took me a second. CO2 and H2O2. Hydrogen peroxide. Okay. So we're looking for the molecules are non-linear. Right, we've done this one before. We did that one earlier. That's linear. Okay. We've done carbon dioxide before also. That's linear. H2O2 is double bent. We've done that one in a previous exercise. So that was not linear. N3 minus, let's do that. So nitrogen is 5 valence electrons. It says 7 there, but there are only 5 valence electrons. So that's 15 plus 1 for the charge. So we have 16 electrons. And we have nitrogen, nitrogen, nitrogen. That's 4 is 12. And work from the outside in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then we need an octet, right? We only have 2, 4 here. So the best way to balance it. All right, so we have, remember the formal charge calculation? Don't remember that? I think we did that. The best way to get the minimized formal charge is to move 2 of these over here and 2 of these over here. Not to move 2 pairs over here and make a triple and a single. That would give you a positive formal charge on one side and a negative on the other. This side, they're balanced. So 2, 4, 6, 8, 10, 12, 14, 16. This has two groups. This is linear. Okay. Acetylene. We've done acetylene before. That's linear. Was that the question? Oh, question is non-linear. Okay, so we just need to do this one. Nitrogen in is 5, and 2 times 6 is 12 plus 1 for the charge. Oh. Boo-boo. Got to put that negative there. Oh. Sorry. I hope you're in pencil. If we've got 15 plus 1 is 16, and we put nitrogen, that's minus 4 is 12. Okay. Then we put, 12 electrons. Is that right? We do that right. 4. Yeah, okay. So that's okay. Like that. Okay. Oh, I think I got it right. Yeah. Now I'm panicking for a minute. Yeah, we just make a double there and a double there. 2, 4, 6, 8, 10, 12, 14, 16. Yeah, we're good. And that has a charge.
So it was right?
Yeah, I was right the first time. Sorry.
Okay, make sure I didn't erase it yet.
Okay, that's a good idea. Okay, so now we got 5 and 2 times 6 is 12 plus 1. So that's 18 electrons. We have nitrogen, oxygen like that. So that's minus 4 is 14. So 2, 4, 6, 8, 10, 12. That's 12. That means we got 2 more electrons to go. We have to put them here. Then we're going to make an octet. So this is one of those cases where it can either come from this side or come from this side to make a double bond. So that's a valid Lewis dot structure. It would resonate between this one and the other one would have a double and a single here. But for determining the geometry, it doesn't matter. You just pick one, right? And this has a negative charge, and this is going to be trigonal planar. Like 1, 2, 3 groups. Okay, so the nonlinear ones are this one and the last one. So NO2 minus and H2O2 is C. Those are the nonlinear ones. Okay. All right. That's 36. And we'll scroll down to 38. And we're looking for molecular structure of BRF6 plus. BRF6 plus. Okay. Well, they're both halogens. So it's 6 plus 1 is 7 times 7 is 49 minus 1 with a plus charge. Okay. So we got 48 electrons. Now we put the BR in the middle. 1, 2, 3, 4, 5, 6. There we go. Fluorine. So it's 2, 4, 6, 8, 10, 12. 36. 2, 4, 6 to make an octet. Right? 6 times 6 is 36. So we used them up. So what's the regular structure for a 6 groups? Octahedron. Right. That would be C. Okay. We don't have any lone pairs to throw in there. So the electronic structure and the molecular structure are exactly the same. for this one. Oops. 39. Okay, what type of structure does xenon oxidifluoride molecule have? Okay. All right, xenon has 8 because it's a halogen, because it's a noble gas. And 6 for oxygen, and 2 times 7 is 14. And so that's 28. 28 electrons. Now, who's going to be in the middle? Whenever we form a compound with a noble gas, those elements are in the middle. So just memorize that one. That one goes in the middle. Then we got an oxygen, and we got 2 fluorines. 2, 4, 6. So that's 22, 2, 4, 6, 8, 10, 12, 14, 16, 18. 18 needs 4 electrons left over. So those 4 go here and here. Let's see if we got, we started with 28, 2, 4, 6, 8, 10, 12, 16, 18, 20, 22, 24, 26, 28. Okay. So how many groups we have? 1, 2, 3, 4, 5 around the center, which is trigonal bipyramid, right? Which means we've got a triangle in the center. We've got something up here and something down there. And these lone pairs are going to go here. Let's put this pair in the back. And then the fluorines are probably opposite one another. And oxygen is out here. So when we look at does it say molecular structure? Type of structure. Okay. I'm looking at the answers too. Because the trigonal bipyramid is the electronic structure. But the molecular structure, cover that up, and watch where the bonds go. You got a bond in here from xenon to oxygen, and 1 to fluorine here and 1 to fluorine there. That's a T-shaped molecule. Okay. That, okay, the key here is 38 says molecular structure. 39 says what type of structure does the molecule have? Right, so we have to assume that it's actually talking about everything except the lone pairs. (44) Okay, select the correct molecular structure for, let's see, there's a special name for that one, silane. Right. Methane is CH4, SiH4, silane, methane silane. So actually we could draw this one. Well, let's do the whole thing. We got 4 here, electrons here. Silicon's like carbon, it has 4. So we have 8 valence electrons. Silicon here, hydrogen, hydrogen, hydrogen. That's it. We used them all up, 2, 4, 6, 8. That's a tetrahedron. And they're no lone pairs. Okay. That would be B. 46. Select correct molecular structure for BeCl2. Okay. Beryllium, which has 2 electrons, and 2 times 7 is 14, so we have a total of 16 electrons. Beryllium's in the middle, right? It's farther to the left than chlorine, so we put it in the center. The more metallic goes in the center. And we got chlorine and chlorine, so that's 4. 12, 2, 4, 6, 8, 10, 12. Now, can we make a octet for beryllium? Yeah. We can move these two over here, move these two over here. So in this case, beryllium doesn't have to be deficient. And that's linear. Right? 2 groups is linear. All right. How about 48? Let's see. Xenon difluoride. That's 8, and this is 14. 2 times 7. That's 22 electrons. Okay. Xenon in the middle. Fluorine, fluorine. 4, it's 18 left over. 2, 4, 6, 8, 10, 12. Minus 12 is 6, right? Yeah. 2, 4, oops. 6. Okay. 1, 2, 3, 4, 5. 5 groups around the xenon is trigonal. It's trigonal bipyramid electronic. So we're going to have this triangle again. Here, the xenon in the middle. And we've got 3 lone pairs. They all go on the triangle. And the fluorines go up here. So that is a linear molecule. Is that one of our choices? Yeah. Oh, it asks us, and what is, let's see, how many pairs of electrons around xenon? 3. 1, 2, 3 pairs around xenon, and it's linear. So that's why the answer is C. Okay, 49. Choose the member of each set that best matches the label. Okay, we got beryllium and barium. Beryllium, barium. And we want to know the more metallic. Repeat. The more metallic an element is, the lower its electronegativity. So the more metallic goes from upper right to lower left. So beryllium and barium. Barium is below beryllium, so this one should be more metallic. What we're saying by more metallic is it wants to give up electrons more readily than beryllium does. More covalent. Okay, so the next one is N2O, laughing gas, and magnesium oxide, solid. And what's the difference here? More covalent. That's obvious, right? Because this is a metal, non-metal, and this is non-metal, non-metal. That means covalent. Okay. And then highest electronegativity out of O, S, and Br. Okay, electronegativity. Oxygen, let's see. Let's just draw this part over here, right? The transition metals are over here. So we got oxygen here. We got sulfur below it, and we got bromine down here. And so electronegativity increases from bottom to top and left to right. So I would say this would be the most electronegative, oxygen. Highest electronegativity, oxygen. Yeah. So let's see. It'd be Ba into O and O. Ba into O and O. E. Yeah. Okay. 50. Okay, let me see here. Get that out of my way. Use the bond energies given below to calculate the enthalpy change for the reaction. Right, so here's our target reaction. I'm thinking Hess's law. HCN plus 2 H2, they even balance it for us, it's nice. And that yields what? CH3 and H2. Is that a gas? It's a gas. Okay, and we want to know the delta H, right? Yeah, delta H. Oh. No, with the information given, bond energies, no, we're not going to use Hess's law. We're going to use this formula. Like delta H equals the sum of the bonds broken. Right? Yeah, sum of the bonds broken. Broken, I'll just write it in like that. Minus the sum of the bonds formed, right? Okay. So we need to know something about the structure here, right? To tell what bond is which. So this one we've done before. We've got those bonds, and I'm going to leave lone pairs out. They don't matter. We got a single bond with hydrogen here. What we have here is carbon with these 3 hydrogens. That's the way organic molecules are written. And then this one with a hydrogen here and hydrogen there. Okay, so bonds broken. We're breaking a carbon-hydrogen bond. Carbon-hydrogen is 412. So I'm going to do this. These are the bonds broken. And then let's add up carbon triple to nitrogen, 891. And these are all kilojoules per mole, aren't they? Yeah. And there's 1 mole of each one of these, right? So that's the value. And then we have 2 times the hydrogen-hydrogen bond, which is, where'd it go? There it is, 432. Okay. Then we're going to subtract the carbon-hydrogen bonds. We got 3 of those. 3 carbon-hydrogen bonds. 413. Okay. And then we're going to add to that a carbon-nitrogen bond. 305. And then we've got 2 nitrogen-hydrogen single bonds. There it is, 391. Okay. So I'm gonna need a calculator for this.
Where'd you get the 412 from?
Did I read it off the list?
I don't see 412.
Oh, 413.
Oh.
Yeah,
I just
carbon,
checked.
carbon hydrogen. 3 times those, 1, 2, 3.
On the other side, the first one.
Oh, this one? That should have been carbon hydrogen,
So it should be 413.
413.
Okay.
Yeah, you're right. There we go. All right. 413 and 891 and 32 plus. So this is 1755 kilojoules. And we're subtracting 413 times 3 plus 305, 391 times 2. Put that together. This is 2326. Is that what you got? So that one I just subtract. And the delta H I calculated was minus 571 kilojoules. No, I did something wrong. Let's see. Let's do 2 times. Did I get all these right? This is
First.
the carbon hydrogen. Carbon hydrogen 413, that's right. 891 for carbon triple bond nitrogen, yeah. And then 2 hydrogen bonds, 243. So those are right. How about these? Yeah, 314, just like that one. 413 times 3. And then carbon nitrogen single bond, 305. And then 2 times the nitrogen hydrogen bond.
Your calculation was wrong for the first part. You might have.
This one?
calculated Wrong, yeah.
Okay. Let's try that again. I'm going to do this one first. 432 times 2, and then add 891 and 413. This is 2168. Okay. And then 2326. Like I said, that's minus 158. That looks better. I would blame it on the calculator, but you know, it's like any computer, garbage in, garbage out. 51. Now, if we've been given different reactions with delta H's, we'd have to use S's law to get there. But I think that way was easier. Okay, 51. 51 is nice because it tells you what each one of those reactions means. And to calculate the change in enthalpy for this target reaction, which is 2 lithium plus 2 HBr in gaseous form yields H2 gas plus 2 lithium bromide solid. Calculate the change in enthalpy. We can treat this like a Hess's law problem. We can actually take the first one. Lithium solid to lithium gas. Right? We want to get rid of the lithium solid. Excuse me, we want to keep the lithium solid. So the lithium solid to lithium gas as written, which is the energy of sublimation is 166 kilojoules. So this is 166 kilojoules. Right? We want delta H for this one. Right? That's good the way it's written. So we got this and that done. And next, the next one, HBr gas. HBr gas. There it is. It's on the correct side. Do we have the right number? Oh, no, we don't. We need 2 lithiums. That means this should be 332, right? Right, because we need 2 of these. 2 there, 2 there. Use that 2. And now it's correct. Next, HBr. HBr goes to H and Br. That's the bond energy for HBr. So if we do HBr gas, and it produces H2 gas, right? No, it produces H gas, sorry. H gas plus Br gas. But we need 2 of them. Right? 2, 2, and 2. So we need to double that value, 363 times 2. Which is 726 kilojoules. Yeah. Okay, so we got that one. We got this one taken care of here. Okay, next, how about lithium gas goes to lithium ions? Lithium gas right here goes to lithium ions. All right, if we put lithium, right, there's no lithium gas up here, is there? So what we need is lithium gas on this side to cancel that one out. So as written, that looks like a good choice. Lithium gas goes to lithium ions. What's the electron? Only we need two of them. Two, and two. So what's the value for that one? 520. So 520 times 2 is 1040 kilojoules, right? Let's see. Some of them have signs. Not yet. Those are all positives. Positive, positive, positive. Okay, so we actually got rid of this one right here. Okay. How about bromine to we're electron affinity of bromine, because we have to have a bromine minus in order to make that solid. We got the lithium here to make the solid. So the bromine is actually going to add bromine gas plus an electron. Makes bromine gas with a minus charge. Right? And we need two of them. 2, 2, and 2. So that one, the electron affinity is minus 325. So it'll be minus 650. We multiply that times 2. Okay. What does that do for us? Well, let's see. Gets rid of this one. There. Okay. What's the next one?
So I can get rid of the 2 electrons too.
Yes, thank you. Yep. Let's see. Lithium ion plus bromine ion makes lithium bromide. Lithium ion gas plus bromine ion gas yields lithium bromide solid. But we need two of them. So we got to do a 2 here, 2 here, 2 here. And the value minus 809. What's 2 times minus 809? 16, 18. Did I do that right? I think I did. Okay, so that cancels this one. And it cancels this one. And it gives us this one. Okay. What's the last one? H2 gas yields 2H gas. H2 gas needs to be on that side. Because we're keeping it. So that means on this side, we need H2. Oh, excuse me. Not H2. We need 2 H's. This is the H bond to energy. Yeah. So it's 432 if we wrote it the other direction. So it's minus 400. H2, H2. So we've got that one and that one. Okay. So we get lithium here. That one, 2 H's. Cancel. Got that one canceled already. Those are gone. Those are gone. This one we keep for that one. And this one we keep for this one. Okay, so I think that's everything. Now we just add those together. Let's see if I can do that. 332 is positive. 726. 1040. Minus 650. 18 minus 32 minus. So I get, I did this right. Minus 1538 kilojoules. Okay. What did I do wrong?
I just had the negatives instead of minus and anything. Like I added the first box and then I put plus -50 in my calculator and then plus negative whatever.
Okay.
Gave me the -6.
Let's see. Let me do that again. 332, 726, add that, and 1040. At that. So this is 2098. This one, 650, 16, 18, 432. Did I multiply this one times 2? No, I didn't. That's it. No, I didn't do that one. I'm not supposed to do that one. Just change the sign. So this is minus 27, 1, 2, 3, 2700. Right? Okay. I can already see we're going to get a different value than I got before. Minus 602. There you go. Check my math. Answering my earlier question, no, I can't calculate that. We did that one first because 52 requires an understanding of what those abbreviations mean. Do it. I'm going to run out of time. So what do those abbreviations mean? Well, the first one doesn't have an identifying mark. Rubidium solid to rubidium gas is sublimation. So the first one is sublimation. Actually, not there. We want the target equation up here. We're headed for calculate the lattice energy for rubidium chloride from the following data. Okay, the lattice energy. What is the lattice energy? Well, the lattice energy is the energy you get back when you combine rubidium, 1 plus, gas, plus, what's the other one? Chloride. Chloride, gas, and you make a solid. Rubidium, chloride, solid. That's the target equation. That's the lattice energy. So what do we have to go on? We have a rubidium solid and rubidium gas. So I'll just put them up here. Rubidium solid to rubidium gas has a delta H of 85.8 kilojoules. Okay, we might have to do some modifications to get them to work. So I'm going to leave a little bit of space in there. IE1, ionization energy, first. So this is ionization energy is rubidium gas yields rubidium ion gas plus an electron. That's first ionization energy, 397.5. Okay, the next one, BE, bond energy. The bond energy of chlorine is the gas yields 2 chlorine atoms gas. We're not making ions, we're just breaking the bond. And that was 226 kilojoules. Okay, delta HF, heat of formation. Right, remember how to do the formation? You start with the compound as a product. Right? RBCl in its most stable form is a solid. Right? It's an ionic compound. And then you work backwards. You say, how many of these do we need? Well, that's a +1, that's a -1, so that's good. So we got the most common form of rubidium at atmospheric. I mean, if we're going to make that out of that, we need an ion. And this would be, okay. I paint myself into a corner. This would be, no, not that. This would be, rubidium is a metal. So it'd be solid at room temperature and pressure. And chlorine would be a gas. There you go. But we only need 1/2 of this. So that is the heat of formation for rubidium chloride, -431. And then the last one is electron affinity, EA. Electron affinity of chlorine, which is gas plus an electron yields chloride ion gas, and that energy is -332. Okay, so now we've got all the information extracted from that table up here on the board. We need to see, how do we get from here to there? We need rubidium ions on the left. Right? We need rubidium ions on the left. That means we've got to put rubidium plus the gas plus electron yields rubidium gas here. And this one has to be -397.5 kilojoules. So I'm going to cross that out so we don't use it again. Okay, that takes care of this one right here. How about chloride? Chloride here. That needs to be on this side also. So chloride minus gas yields chlorine, atomic chlorine plus an electron. And that's going to be +332. Okay, that takes care of this one. That. Now, rubidium chloride solid, where is it? Right here. That's one of those, one of those. That one's good the way it is. Right, so we use this one, we use this one, and we use this one. Okay, so these three give us everything we've got up here, but we've got some extras. We've got some extra components in here that we have to get rid of. Electrons, one's there, they're gone. How about rubidium gas? Well, rubidium gas is now on this side, so that one has to be reversed. And needs to be -85.8. Okay, so that gets rid of rubidium gas here, and rubidium solid. Where is rubidium solid? Oh, yeah, well, that's one. Where's the other one? Here. Wait a minute. Yeah. That's right. We were keeping this one. Yeah, okay. So we need to get rid of this rubidium solid. Rubidium solid. There we go. Okay, so that one's used up. Let's see. rubidium. That goes up there, good. Okay, how about this chlorine? We need a chlorine minus. Chlorine minus, we gotta get rid of a chlorine, atomic chlorine here. Right. So we gotta keep it this way because that one feeds this. So this chlorine here needs to be, this needs to be reversed and take a half of it. Because we only need one of these. Yeah, we only need one. Reverse it and take half. So take half of this, which would be one chlorine on this side, yields a half of a chlorine molecule on this side, and then we reverse that and take half of it. Okay, that takes care of that one. And this half a chlorine goes out, and this chlorine goes out. And I think we got it. We canceled everything we didn't need, and we kept everything we did need. So let's see what we get. Yes. 34. Don't see the cat. Still want from this one. Okay. 85.8, change the sign. 397.5, change the sign, add that one in. 13. 131. And then add 332 plus. So I got 695.3. Round it off, 695. That's a negative. 695. Okay. That is the lattice energy for that molecule for rubidium chloride. I know I took a lot of time. Oh. Are we getting close to the end?
I only have two more.
Okay. Hope they're not very long. Oh, okay, 53. In spite of the large electronegativity differences between the bonded atoms, beryllium chloride has no dipole while sulfur dichloride does. All right. So this is 53. We got to compare these two and there. Right, so beryllium is 2 plus 14 is 16 electrons. So we got, excuse me, beryllium, chlorine, chlorines, that's 2, 4. We did this one earlier, but I forgot. It's coming back to me. So that's 12, 2, 4, 6, 2, 4, 6, 12. Okay, so we're going to use here like that, here like that. Okay, how about sulfur dichloride? Okay, sulfur is like oxygen, it's got 6, and then 14 from the chlorines, which is 20. So we got sulfur in the middle, got chlorine and chlorine. That's minus 4 equals 16, 2, 4, 6, 8, 10, 12. 4 electrons, 1, 2, 3, 4. So this is going to be a bent molecule. Well, it's tetrahedral electronic, but it's going to be a bent structure. Like this, kind of like water. And we're going to have chlorine is, this is the one that we weren't sure about. It's definitely polar. Because even though it's a tetrahedral electronic structure, it's a bent molecular structure with unbalanced polarity. So this one's polar because it has these electron pairs, whereas this one does not have any unused electron pairs. It's linear. So the electronegativity, this direction and that direction, cancel one another out. This is non-polar. Right? So that's what I'm trying to say in that red explanation. The overall dipole depends on the geometry. And the geometry for beryllium dichloride is, actually beryllium chloride, is nonpolar because it's linear. And sulfur dichloride is nonlinear, and that gives you a net dipole. Okay. Got it? Getting there. Okay. One more. Uh, 54. Draw the Lewis structure for ICl4 minus. ICl4 minus. So we have 5 halogens, which means 5 times 7 is 35. Plus 1 for that charge. So we have 36 electrons. We're going to have iodine in the middle. It's a lower electronegativity than chlorine because it's below. So it goes in the middle. We have 4 chlorines, 2, 4, 6, 8. 28 electrons, 2, 4, 6, 8, 10, 12, 15, 16, 18, 22, 24. So we have 4 left over. 2 there, 2 there. Okay, so this has 1, 2, 3, 4, 5, 6 groups, which means electronically it's an octahedron. Right, and that means we've got a square in here in the center. And we've got something down here and something down there. And iodine goes in the middle. Now, where do the lone pairs go? In the octahedron structure, the lone pairs go at apex. So you put one here and one here. And the other chlorines stay on the square. Okay? So this structure is going to be a square planar. This is electronic structure and this is molecular structure. It's square planar. I think that answers the other questions. Oh, and polarity. Right. These lone pairs cancel each other out, and these guys are at perfect 90-degree angles from each other, and their polarities are going to be toward the chlorines, but they're the same magnitude, pointing to regular positions on a square, and they cancel each other out. So this is a non-polar molecule. And we know that's true because it's been measured. This molecule has no polarity. I think that's it, isn't it? Yep.